Okay, in this video we are going to work through this problem. This is a pretty difficult problem, and it's probably difficult enough that I wouldn't give you something quite this difficult on an exam or a quiz, but you know, it's worth going through a more difficult problem just to see how it's done. And it's not so difficult that you couldn't do it. There's one little wrinkle somewhere along the line that most people probably would not get without a lot more math. So here, the question is, again, pretty simple to write down. Write the rate law for this reaction of nitrogen gas mixing with oxygen gas. And there's a bunch of sample pretend experimental data here. So what we're trying to do, the rate law, if you remember, is just the rate or the speed of the reaction is going to be equal to some number called the rate constant times the concentration of N2 at the beginning of our experiment raised to some power times the concentration of O2 at the beginning of our experiment raised to some power as well. And these two numbers, the power numbers, they don't necessarily have to be the same thing. They don't have to be the same number. So we have to do these experiments to try to figure out what these exponents are. Once we figure out what the exponents are, then we have to do a second step and figure out what the rate constant number is. We're not just going to call it K, we're going to put a number on it. And it is going to have some weird units if I remember correctly. This is what we're shooting for. First thing we're going to do is figure out these question marks. First thing we're going to do is compare these two experiments here, experiment number 2, experiment number 3. If you notice, experiment number 2 and number 3, the concentration of O2 at the beginning of our experiment is the same. So this thing doesn't change between experiments 2 and 3, but the concentration of N2 at the beginning of our experiments does change. So what we are doing when comparing experiments 2 and 3 is we're trying to figure out what number is going to go here for the N2, because the N2 is the only thing that's changing in this case. If you start out with experiment 3, the concentration of N2 is 0.01 molar, and in experiment 2, the concentration of N2 at the beginning is higher. It's 0.04 molar. And hopefully you'll agree, this number here is 4 times bigger than this number here. So concentration of N2, if the concentration of N2 goes up by 4 times, what happens to the speed of the reaction? Well, we want to compare 500, which is the speed molar per second, to the speed in experiment 3, which is 125 molar per second. You'll agree that 500 is bigger than 125. And if you take 500 and divide it by 125, you'll see that this number is also 4 times bigger. The speed of the reaction is 4 times faster in experiment 2 when you compare it to experiment 3. If we make N2 concentration go up by 4 times, according to these two numbers, the speed of the reaction also goes up by 4 times. So what that means is speed of the reaction is proportional to the concentration of N2 to the first power. In other words, if I make the concentration of N2 go up by a certain amount to the first power is still that same certain amount, which means the speed will also go up by the same certain amount. If I make the concentration of N2 get 100 times bigger, 100 times bigger to the first power is going to make the speed go 100 times bigger. So we know that the exponent that goes next to the N2 is going to be a 1. So that one was pretty easy. Here's the more difficult one. Now we're going to compare the results of experiments 1 and 2. If you look at experiments 1 and 2, this time the concentration of N2 is not changing, so we're not messing with N2. We are messing with the concentration of O2. And in experiment 2, it's a certain concentration of O2. In experiment 1, it's twice as much. So concentration of O2 goes up 2 times. And if you look, the speed also gets bigger. The speed is 707 molar per second compared to the speed in experiment 2 is 500 per second. And you'll agree that 707 is bigger than 500. So, you double the concentration of O2, got twice as big, the speed got bigger. But it didn't get twice as big, because twice of 500 would be 1,000, and 707 certainly ain't 1,000. So if you take 707 and divide it by 500, what you'll get is the speed went up by 1.414, or approximately 1.414 times faster. If you double the concentration of O2, the speed of the reaction gets about 1.414 times faster. I'm going to write that here. In this one, I don't expect you to recognize this relationship, although some people might. Basically, if you double this number, and this number only gets 1.414 times faster, that means that the speed goes up by the square root of how much the O2 goes up. So this number here, if you remember from very early in this collection of videos, square root of something can be written as something to the 1/2 power. So the number that goes next to the O2 as an exponent is going to be 0.5 or 1/2. And that's the part that I don't expect you to recognize. I would never throw a square root relationship at you, but I'm telling you right now that if you double something and the speed goes up by 1.414, that means the speed is going up by the square root of whatever the O2 concentration is going up by. And square root can be written as a 0.5. So we can write the beginning of our rate law equation like this. The speed of the reaction is going to equal the concentration of N2 raised to the first power times the concentration of O2 raised to the 1/2 power, which just means times the square root of the concentration of O2. And then all of that multiplied by some number, which we're going to call K. But I don't want to just call it K, I want to actually give it a number. So we're going to figure out, step 2 here is to figure out what the K number actually is. And this part is easy, although the units are going to look weird. All we have to do is we can pick any of the 3 experiments. So I don't know which one I'm going to pick on the next page, but we could pick these numbers and we could plug them in, right? This N2 concentration would go there. This O2 concentration would go here. This speed would go here, and then we can use algebra to figure out the last missing piece, which is K. So it looks like I picked experiment 2 here. So what I did was I said I want to use the numbers in experiment 2. So the concentration of N2 in experiment 2 is 0.04. So I wrote 0.040 molar there. And if you look, it's raised to the first power. Concentration of O2 in the second experiment is 0.010 molar. So that's there, raised to the 1/2 power. And the speed of the reaction, the initial speed of the reaction in experiment 2 is 500 molar per second. And so now all we have to do is simplify things to figure out what our K number is. So one thing that I did, so this is just the beginning of simplifying this equation up here, is I wrote 500 molar, and then second to the negative 1 power, which just means per second, is equal to these numbers here. So I haven't really changed anything yet. This is a little bit tricky here, going from the second line here, line number 2, to line number 3. Remember, 0.5, something raised to the 0.5 power is the square root. If you take the square root of 0.010, you'll get 0.1. That's the square root of 0.010 is 0.1. And so this square root has been applied to this, but it also has to be applied to the unit. So if I simplify this part over here, what I'm doing is I'm doing 0.01 square root of that, and that's 0.1. But I'm also doing the molarity number to the 0.5 power, and so we're going to be stuck with this weird unit of molarity to the 0.5 power. But we're just stuck with it. That's sort of what we have to, that's the unit that we have to use to simplify this equation. Next thing we're going to do is we're going to simplify this, but there's not really much to simplify because it's going to be 0.040 to the first power, which is just going to be the same number, and it's going to be molarity also to the first power, which just means it's going to be the same number again. So that's going to be 500 molar per second is equal to the rate constant times 0.040 molar to the first power times 0.100 molar to the 1/2 power. And so we can simplify these numbers by multiplying them together. We can do 0.040 times 0.1, and that's going to be 0.004. Because if we do 0.040 times 0.1, we're going to get 0.004. But we also have to multiply the units together. Molarity to the first power times molarity to the 1/2 power. If you remember from the rules at the very beginning of this collection of lectures, we add the exponents. So it's going to be molarity to the 1.5 power. So 500 molar per second, that's our speed, is going to equal the rate constant times 0.004 molar to the 1.5 power. And this looks crazy, and it kind of is, but this is just what you have to do to get your K number. Now the only thing that we have left to do is we need to get the K number alone, which means we need to get rid of this business, which means we need to divide both sides by 0.004 molar to the 1.5 power. We have to multiply the left side by 0.004 molar to the 1.5 power to get them to get the left and right sides to stay equal. And in that case, we'll have K is equal to all of this, because the 0.004s and the molars on the right side will cancel away. And we're going to do 500 divided by 0.004. And 500 divided by 0.004 is 125,000. And the only thing left is the units. This is a little bit weird, but in the numerator we have molar to the first power, and in the denominator we have molar to the 1.5 power. And remember, very early in this collection of videos, in the background section, I said that if you have the same base, so we have the same unit, and you're dividing by powers of the same base, you take the top power and you subtract away the bottom power. So the unit is going to be molar to the 1 minus 1.5, and 1 minus 1.5 is negative 0.5. So the unit here will be molar to the negative 0.5, which is a little bit weird, but that's what it is. And also the second to the negative 1 power doesn't cancel anything. So this is our K number. It's 125,000 with these really weird units. Molar to the negative 0.5 and also seconds to the negative 1. Those negatives basically just mean that the units, molar unit and the second unit, are in the denominator actually. That's what the negatives mean. The 0.5 here means square root of molarity. But you can leave it like this. This is basically the answer. The rate constant is 125,000 molar to the negative 0.5 seconds to the negative 1. And if you wanted to put it back into the rate law equation, you would basically say the rate of the reaction is equal to 125,000 molar to the negative 0.5 seconds to the negative 1 times the nitrogen concentration to the first power times the oxygen concentration to the 1/2 power. And this would be our complete rate law equation. So that was it. That was a pretty tough problem to work through. Certainly the square root bit I don't expect you to be able to do. But that's about it for this video. See you in the next video. Bye-bye.